Alright, continuing this series of videos, redoing, sort of, Professor Lewin's 802 series of lectures on mostly electrical and magnetic effects and such. Anyway, yes, I think I'll do a quick drawing just to clarify, which might have been a little bit of confusion in the last video, but this whole conductor right-hand rule thing, that just becomes a little bit of a problem. And so when we do this, into the blackboard kind of thing, the trick is that you could, depending on how you look at it, these things aren't the same exactly in terms of this clockwise and counterclockwise motion of defining something's charge. So the trick is they're basically saying, okay, you go clockwise and clockwise, but clockwise is just a way of saying that if there was to be a magnet or something, then it would have a direction. So you'd have a south end and a north end of a magnet would be sort of represented by that direction of that arrow. And then if you line up those magnets that way, you'll sort of notice that although these are like charges, they have opposite magnetic poles. So from the inside and the outside, you get, it's only in certain. So looking at it this way, yes, it's the same thing. The arrows are going the same way. But if you look at what the magnet is doing, then you can see that its likes are going to end up attracting, because you're going to have a positive facing a negative. And so it just gets a little bit complicated, because you have to think about its polarization that this arrow represents. So when he says something like the B field goes this way or something, the thing that's missing from that description is the fact that the polarization is going to be it's going to have a definite sidedness to it, dictated by that arrow. It represents a dipole. It doesn't represent monopoles. And the dipole is part of this more simple thing drawn with an arrow. So instead of drawing a dipole, so instead of acknowledging that the polarization is the thing that's obeying the right-hand rule, and that it's always going to have polar opposites left to right. So if the top is red-black, then the bottom's going to be black-red. And the same for the sides. If one side is north-south, then the other side's going to be south-north. And that's the part that gets lost in all of this. So I did it the wrong way. So it'll just have to be a little bit out of position. And that's where the confusion comes in, is you always have to keep thinking about, okay, the magnets, even though everything's the same here, same dot, same arrows, the magnetism will be exactly the opposite viewed from inside. So I just wanted to point out why I was having a little trouble, because I had to think about which way the magnets were, and I was failing to do that. I was just looking at the dot and the arrow and saying, well, how can that be? They'd end up repelling, when obviously they wouldn't, because it'd be plus to minus. So they really are opposites, even though they look like they're the same. They're really opposites in that circumstance. Alright, I think that is enough of a clarification. And so, on to the video and such.
Now, I want to show you what magnetic field we can get with this baby, which is exactly what I had here on the blackboard. It has 2800 windings, and we're going to run a current which is something like 4.5 amperes. But I'm going to tell you what that current is, because I have a current meter there for you, and I also have a meter which indicates the magnetic field. The lower one is the current meter, and the maximum current that you see there, the 3 would be 6 amperes. And the upper one is calibrated in such a way that if it is full scale, you would have 300 Gauss. So 3 is 300 Gauss. And I have a probe, a magnetic probe. We never discussed how that works. We call it the Hall probe. And this Hall probe allows me to measure the magnetic field in the vicinity of this solenoid. It's even sign sensitive. If the magnetic field is like this, it will go to the right. If the magnetic field is like this, it will go to the left. And so this allows us then to be actually quite...
Probably has something to do with little magnets in it. You know, magnets. The only real way to detect magnetism is to basically probe it with charge or magnetism in some form. No, I think that's enough. He doesn't tell what the core of this thing is made of. You know, what the wire is wrapped around. Be a little curious what that is.
Quantitative and evaluate the magnetic field near the opening of the solenoid. Then we can go in there and we can also probe the outside. So I'm running now a current. Let's look at it. That's the bottom meter. So that is about 4.8 amperes. I assumed it was 4.5. It's a little higher. And here comes this probe. And I'm now about a foot away from the entrance. And you see nothing. And I come closer to the entrance. And the magnetic field begins to show. Nowhere nearly constant yet. I'm now entering 100 Gauss. I'm going in deeper. 200 Gauss. Even deeper. And deeper.
Alright, so the deeper you go, obviously the less, the ends are going to be where some of it is leaking out. So some of it doesn't reflect as many times inside, not as much reflection between the wires because the end wires aren't having any reflection. So you don't have reflection between the wires, support between the wires, pressure support essentially. I mean, the wires are radiating a force also into the next wire, and that force is just adding pressure to the other wires, magnifying their effect, and then you have the reflections on the inside. But once you reach your equilibrium, that is your maximum amount of magnification, then it becomes constant. So in the middle, it's constant.
And now I have about 240 Gauss, and notice, as I go in further, it doesn't increase. It's more or less constant. Amazing that it's more or less constant. And when I come out here, I move it back and forth about 20 centimeters. If I came in from the other side, you would simply see a reversal in the sign, which is not so interesting. So you see 240 Gauss but the other direction because this probe is sign sensitive. I can now also show you that if I come on the outside of the solenoid, you see nothing. So indeed, our assumption that the magnetic field is very low outside a tightly wound solenoid was a very good assumption.
And again, it's only based on the fact that it's not being magnified. It just gets to have an effect once. So all the radiation, so if you thought about the wires radiating, you can sort of understand the radiation is being reflected on the inside, no reflections on the outside. So it only has one shot to hit on the outside, so it looks weak. It's like two suns facing each other, and if you could imagine the two suns were reflective, like all the energy they produced reflected off of each other, you could imagine it'd be so much brighter between them than on the outside of them.
Very well. You've been asked, and the deadline is Friday, 4 p.m., to explain the behavior of the Kelvin water dropper. And I decided to give you a little bit of help on that. Most of you may already have figured it out, but those who haven't probably won't figure it out between now and Friday anyhow. So I might as well tell you. That water dropper, called the Kelvin water dropper, is an amazing battery. We've seen it before, we know what it's doing, but I will go over that again. We have here buckets A and B. Water comes down from above, water runs through. You see the water there, it runs out. And we collect these water drops here in bucket D, it's a conductor, and this water is collected in bucket C, it's also a conductor. And the paint can A is connected to C, that's crucial, and the paint can B is connected with D. And here there are two balls which I can bring close together. I run water, and after a while I see a spark here. I can even see a spark when the distance is something like 6 millimeters, which would be about potential difference of about 20 kilovolts. How does it work? Well, water has a pH of 7, and That means 1 in 10 to the 7 molecules is ionized. So I have OH minus and I have H plus. Those are going to be the current carriers. The ions are doing the work here, are doing the job. Let us make an enlargement here of can A. And can A, let us assume that purely by chance, it has a little bit of positive charge on it. It could be negative, but I'll just assume it's positive for now. In either case it will work, you will see. Just by chance.
It depends, obviously, on what can also, has the higher potential. So if can B has a higher positive potential, then it probably will win in deciding who's going to be positive and who's going to be negative. But like in all these cases, something will decide the circumstance. There's some deciding factor because it has to go positive, negative. It can't just stay in between.
It's like you have a little bit of net charge. You're not completely neutral. And so this can has a little bit of positive extra charge. And now here is the drop from the spout. What's going to happen? Through induction, through polarization, you get a little bit of excess negative charge here and a little bit of excess positive there, because the positive repels each other and the negative is being attracted. So the H plus goes a little bit up and the OH minus comes a little bit down. But now the drop breaks. And here goes the drop. So it's a little bit negative. So now
So we're back to basically breaking off a dipole, or so the positive moves further up, and so you end up with something that's more negative because it broke a dipole and it created a monopole drop.
A little bit of negative drops come down, and so this becomes negative. But this is connected with B, so B becomes negative. But what do you think is going to happen now with the drops that fall through B? They are going to become positive. Because if B is negative, then of course this will be reversed. The bottom will be positive, the top will be negative. And so those drops now that are going to fall through are going to be positive. So C becomes positive. But C is connected with A. So A becomes more positive.
Right, and they're falling into this bucket on the inside, which means the charge on the outside of the bucket can keep increasing. I don't know if he's going to go into that, but this is sort of like back to the Venn graph. You can keep piling charge on the inside and magnifying the charge on the outside of conductors.
And so A can do even a better job now on these water drops and polarize them even more. And so you get a runaway process. And the whole system feeds on itself until the potential difference here becomes so high that you exceed 3 million volts per meter, and then you get a breakdown and you see a spark. Now you can think of a continuous stream of water as a stream of individual drops. So it also works if you just have a regular stream of water going down. Who is doing the work here? Someone has to do the work.
Yeah, well, the stream of water, you can think of it as individual drops, but that doesn't really go with the breaking the dipole argument of, creating the monopoles of charge. So you have to go back up to the spout, and you have to say the spout is really where the dipole is being created. The spout is the thing that is conductive in some way. It's conductive through the water, even in the spout. And so that when it goes positive to negative, it's going positive negative all the way up through the spout. The positive is up here in the spout, in the tubes above the outlet, and the negative is down is the water that's streaming. And that has to be the dipole. And that's why the two spouts are kind of far apart, is because they have to be able to polarize the water as it comes into that T, and that water's getting polarized before it even comes out of the spout. So his drop example is a nice illustration, but it really doesn't have anything to do with breaking dipoles. It has to do with the fact that you're breaking the dipoles that are very long, the length of the spout.
You have a battery. The battery is being charged, and then it is discharged through this spark. Who is doing the work? Any idea? Have you thought about that? Yeah? Gravity. Very good. It's gravity that is doing the work. We can see that very easily by identifying the current that is flowing and the electric field. How is the current flowing? If negative charge is going down, would we all agree that the current is going up? If positive charge is going down, do we agree that the current is going down?
No, we don't agree that there's currents at all, so that happened already in the spout. You're done having currents. All you have is the negative charges now, and you've created you've broken your dipole, created negative charge that just be like on a little metal ball. The water's now negatively charged. You're just touching the metal ball inside the can at the bottom, and you're just adding more and more charge to the outside of can D or whatever, RC. But there's no currents anymore. Currents are done.
This side of the spout here will be slightly positive and this is slightly negative because the H plus is more abundant here than there.
Right, so that's the key to this whole thing, is the spout is the thing that's going positive and negative, and that's the place where you have your differential. This is where the dipoles are being separated. This is where you're separating into a dipole, and now you're breaking pieces off of the dipole, essentially. Pieces of the dipole are breaking off, and they're all charged. So you've essentially touched a charged thing, and you have the charge now on the thing, and now you're just putting it inside the can.
And so we're going to get a current through the water in this direction. The water has a low but sufficient conductivity because it's ionized 1 out of 10 to the 7 molecules. And so once in a while, if you see a spark here, then you get a current there, but that's intermittent, of course. How about the electric fields? Well, electric fields we know go from plus to minus. So that's easy. We can put the electric fields just in like that. Electric field must here be in this direction. The electric field here goes from plus to minus. C is to plus charge, B is minus charge.
So again, I think he has this mislabeled in the sense that this can is negative. And he's got the spout marked as negative. But frankly, the can has to be inducing the charge, so this spout has to be positive here, because it's negative back here. So it has to be the other way around. Yeah.
And so the electric field is in this direction. Electric field is from plus to minus. This is plus, this is minus. So the electric field is in this direction. Electric field is from plus to minus. The can A.
So again, this is the only place where there's going to be an electric field is between can C and D. All the rest of this stuff there's no fields. There's no fields anyway. There's either pressure or no pressure. There's current or no current caused by pressure.
It was positive, remember? So the electric field is from plus to minus. So that's the electric field configuration. But now look what's happening. Here, the E field and the current are in the same direction. That's fine. Here, the E field and the current are also in the same direction. That's great. But now look at these poor negative ions. These negative ions don't want to go in the direction of E. Negative charge wants to go against the direction of E. But gravity says, sorry, you can't do it. I force you down. And so these negative drops are forced by gravity to go down. Look at this pop.
So again, it's really incidental. The purpose of the cans, the cans that the drops pass through, is just to get the charge up to the spout.
Positive charge. These poor water drops which are positively charged go against the electric field. They don't want that. Positive charges want to go with the electric field. Gravity says, sorry, it's too bad, I force you down. And so gravity is doing the work, so to speak, against the will of the charges. And then the battery charges up and charges up until the potential difference becomes so high there that you see a spark, and you deal with potential differences of something like 20 kilovolts. Remember last time, and you will see that again today, that as the water goes through and as the system charges up, that you begin to see that the water, which starts running like so, begins to spread out. It fans out. You could hear it by a change in the sound, but you can also see it, and I'll make you see it again today.
Which is no different than you being grounded and being next to the Venn diagram with your tinsels, and your tinsels spread out. So even though the water has a very low voltage potential, it's going to spread out because the voltage of the can is getting higher and higher and higher. And so it's creating more and more charge. And the higher the charge, the higher the capacity to magnetically attract. The can A and B are becoming powerful monopoles.
Why is that? Well, that's immediately obvious. If this can is positively charged, but if the water is negatively charged, the negative charge wants to go to the positive can, and so it spreads out. So it's clear that by the time that you reach almost the spark, that water will spread out quite substantially. And you will see that. And then when there is a discharge, it will start running again, narrow stream, and then slowly in time, the water will spread. And so now I will do a
modifications to this would be interesting. Like maybe you could replace can A and B, the hollow cans, with just a half a can or just a metal plate, theoretically.
Series of demonstrations which will support what we know and what we perhaps don't know. Let's first give a little bit of light here, because we will need that. And then I'm going to make it completely dark, so that you get maximum pleasure for your money. And I will first show you here the gap, those two balls. And this time we have a real treat, which we owe to Marcos, who is standing behind the instrument very modestly. This time we have a gauge, a meter, which measures the electric field very close to can A. And the reason why that is nice is that as this system charges up, we just don't have to wait now just until we see the spark, but we can look at the galvanometer there and slowly see it being charged up. And then we get a spark and then it discharges. So you get a lot more for your money. So I propose that the first thing we do is what we did last time, that we simply let it run and see whether we get a spark. There's always air bubbles in the system which I have to get out. Okay, I think I did that. Okay, let's just be patient. Ah, it starts already. Look at the E field. Bang! First spark. Can you see the spark on the screen? Look at it again. There's a spark. And at the same time you see how the electric field goes away, charges up, bang. Charges up, bang. So it starts the whole system charged because of a random positive or negative charge that would be present on one of the cans. What I want to do now is I want to increase the gap between the two balls, and I make it so large that you will never achieve an electric field there of 3 million volts per meter. But somewhere else on the unit, it has lots of sharp edges and sharp points, somewhere else the electric field will reach the breakdown voltage, and so the system will go into discharge, into corona discharge. You will never see sparks, but it goes into discharge. And you can see that because now, I will open the gap now. If you now look at the electric field, it will reach a maximum value, and now it goes into discharge. You see, it begins to sort of sputter a little bit back and forth. So now there is no longer a spark on the balls. You don't see anything between.
Right. It'd be interesting to see if they could find out where that might be. Part of it might be the water that's going onto those cans as it spreads. Because water carries charge fairly well, and it has a very low breakdown voltage. So some of that might be where some of the charge is leaking, and it's just dripping.
The balls, but it is somewhere else. I don't know where there is a continuous stream now of charging.
You have the top edge of the can. The bottom cans have their top edge. Maybe if they folded those edges in, they could reduce some of the discharge.
Leaving the system, and so it's discharging to corona discharge. And so in this mode, you expect the water to be spread all the time. And I will show that to you by switching now to the water. Maybe Marcos, you can improve on the light. I could turn this off, maybe then you'll see it better. But you see that the water is spread, and I will now bring the two balls closer together. I also want to see, of course, the electric field to see the discharge. If I bring them closer together, stopping the corona discharge. There's a spark. And now watch the water. See, the water is now just not interesting. And there it spreads. I'll turn the light off. You look at the water. So slowly the system is charging up. You see the water? Bingo. You can even tell by the water when it sparks. There you go. Now I want to do something real mean. What I want to do now is to raise the spout so high that A cannot reach out all the way to the spout. It's too far away and cannot polarize the water. So the poor battery cannot start. That's a pretty mean thing to do to a battery. But on the other hand,
Yeah, I'm not too sure whether it has to actually get to the spout because it can just go through the water. But, you know, water's not a good conductor, but it's not a nothing conductor either. Be interesting if you did actually put some salts in the water to see if you can even magnify this effect. You know, create 1,000,000 times more ions and see if that really, you know, if you know how much energy you can actually get out of a system like this.
I'm not all bad. What I can do is I can start the system, I can help the system. I use my extrophorus disk, and I'm going to hold my extrophorus disk very close to one spout, temporarily allowing it to polarize the water. And once it starts, chances are that it will feed on itself and go into the runaway. It's not very predictable, but I will make an attempt. So the first thing that I will have to do is, maybe you can zero the E field, yeah, thank you. So the first thing I want to do is to make sure that if we start running water now, that the system doesn't start by itself. Because then I can't be nice to the system anymore. So let's just run some water. I hope that Marcos brought it high enough. And let's see.
Probably should have touched everything. Oh yeah, he's touching it now.
And you can really tell by looking at the, oh, there are air bubbles in the system. I have to get rid of the air bubbles. There we go. Okay. So look at the electric field doing nothing. System can't start. A is desperately reaching out to this water, but it's too far away. It can't polarize it, and the battery can't get going. Oh, yeah, it does get going. Oh, Marcos, we didn't bring it far enough. You have to bring it higher. Oh, by the way, this is interesting. Let's see whether it actually... Oh, boy, this is incredible. This is a distance of about 50 centimeters. And look at it. That is amazing. The little sucker. I had never expected that. Let's give it a fair chance. Let's give it a chance. It's only reasonable. It goes very slowly now. You can see why it goes so slowly, because A, very far away from the spout. But boy, and you can see the water is still pretty normal. Oh man, this is almost cheating on me. We have to raise it a little further afterward. I want to give it a chance to spark. Yeah, the two balls are close enough, so it will probably get there. Boy, this is almost torture for me. Oh, look at that! Look at that! I begin to see the water already. Look at the water. It's already spreading a little. Ah, there it is. Marcos, can you run it even higher? And then we'll see whether we can actually stop it altogether, bring it a lot higher. And then we will make an attempt to start it with some help from a friend. You ready? Oh man, I can hardly.
Gotta wait till you touch the cans.
Okay. Don't tell me that it's going to... It can go to the other direction, of course, because it's a random choice that it has at the start. It's letting me down. Let me see whether I can help it a little. My electrophorus disk. I'm going to hold it here. You know why I held it there? Because I was hoping it would reverse the direction. It doesn't even want to do that. It's really recalcitrant today, isn't it? Hold it here. Negative charge. The reason why you see the sudden change in the electric field is because of the E field probe,
which senses the electrophorus disk when I held it near the spout above B.
It has decided, no matter what. Well, has it really? Has it really made any decision? It's thinking now what it's going to do. Oh man. Yeah! It's going in the direction that I wanted it to go because I held negative charge close to B and I knew that would force it into the direction that it's going now. Oh man! Yeah!
A little animated, a little overexcited for, you know, it's kind of underdeserved maybe. But I guess we'll just finish up. Yeah, there's nothing much to say. That the distance just makes the process slower, so yes.
Well, look, the distance is now, what is it now? Something like 85 centimeters. The system is desperate, but it's doing what it's supposed to do. Physics works again. And we will get a spark because this is close enough. Oh, boy, you got a lot for your money this time. You really did, didn't you? You saw, for one thing, that the system first started up going in one direction and later in the other because there was a random charge which changed polarity, which is something that we cannot always control. But by holding this negatively charged disk close to the spout above B, I forced the polarization in the way that I wanted it. And that's what you're seeing now. We've got to give it a fair chance, and then I'll give you light, and then you have 4 more minutes left to fill out the evaluation. But let's at least give this battery a charge now to lay its egg. The water still doesn't show much of a sign of spreading, but I expect that that will happen very shortly because we've seen this now before. It's slowly increasing the charge on the cans, A and B. It's creeping so slowly that if we wait, you may never be able to fill out your... I'll give you a little light so you can fill out the evaluation, and then we can still let it run and see what happens. So please leave the evaluations here as you leave. And I will keep that going for some of you who have the patience to see what will happen.
Guess they could have told us what happens. But I guess it's predictable. Alright. Alright, so done with another lecture. And such. Sorry, yeah, there wasn't much to comment on, so that is either good or bad news. Guess it's sort of good news that most of what he was saying was reasonable enough. So anyway, till the next time, and